Digital commerce has historically relied on human intervention for every decision, click, and approval. Now, the infrastructure is moving toward fully autonomous systems. This model is known as Agentic commerce. In this framework, AI models manage the entire lifecycle of a purchase or a SaaS subscription. They search for products, evaluate all available options, and execute payments end-to-end, with human intervention entirely removed. This automation relies on the Universal Commerce Protocol, or UCP. It provides the standardized framework allowing AI agents to interface directly with retail and payment systems through multi-step tool calling loops. Because these agents operate continuously over long time horizons, their internal data logs grow rapidly. Every query, tool call, and system response is recorded into a single operational transcript. A single autonomous session can easily scale from a few thousand tokens to accelerate past 1 million tokens in its transcript. The core engineering challenge of agentic commerce is no longer determining if the agent can execute the task. It is figuring out how to secure the massive, unstructured data logs they generate in real time. The current industry standard for securing these agents is straightforward. Developers deploy a secondary, frontier language model to operate as an asynchronous monitor. This monitor scans the agent's transcripts, looking for unauthorized behavior. It searches for actions like data exfiltration or attempts to sabotage internal policies. Developers are operating on a specific assumption. If a model has a 1 million token context window, feeding it a 1 million token transcript guarantees accurate data retrieval and reasoning. New peer-reviewed research from Anthropic reveals a severe flaw in that assumption. They identified a phenomenon known as classifier context rot. As the prefill length of an agent transcript increases, the classification accuracy of frontier models deployed as safety monitors aggressively degrades. When you scale up an agent's autonomy, you increase its transcript length. That increase directly scales down the reliability of the system designed to monitor it, opening a critical vulnerability in enterprise security. The Anthropic preprint evaluated 3 frontier models: Opus 4.6, GPT 5.4, and Gemini 3.1, specifically on long context monitoring tasks. They tested these models using Monitor Bench, a dataset designed to see if a monitor can catch an agent executing a covert attack, such as discreetly disabling a firewall for specific IP addresses. This graphic details Opus 4.6 failure rates. On covert attacks, it misses 1.4% at 16,000 tokens. At 1 million tokens, the miss rate jumps to 12%. For obvious embedded threats, the miss rate spikes from 0.3% at 100,000 tokens to 31% at 1 million. Expanding a model's hardware context limit does not linearly expand its functional reasoning limit. Pushing a massive transcript into a state-of-the-art model actively blinds it to obvious threats. Total token count is only half the problem. The degradation in classification accuracy is highly sensitive to exactly where the malicious action is positioned within the transcript. To test spatial recall, researchers padded a malicious tool call with benign actions on both sides, adding prefill data before the attack and suffix data after it. This chart tracks detection rate against the attack's injection position. As the attack moves toward the transcript center, detection plunges into a deep trough. Positioning 500,000 benign tokens before an attack and 100,000 after creates an operational black hole where recall hits its lowest point. A threat actor or a misaligned agent attempting to bypass security does not need to deploy complex evasion techniques to beat the monitor. The agent simply needs to wait out the clock, or rate of success. The standard engineering reflex when facing a model limitation is to attempt a fix through supervised fine-tuning. The Anthropic researchers tested this mitigation by fine-tuning the monitor's weights on 2 distinct datasets: synthetic needle-in-transcript data and proxy rule violation tasks. Direct synthetic training yielded only marginal improvements on exact match tasks, and the model failed to generalize its reasoning to catch novel threats. Training on the proxy task produced actively negative results. The fine-tuned model's performance actually dropped below the baseline model's ability to detect subtle attacks. Scaling the diversity of the datasets produced the same outcome. More data did not reliably improve the model's capacity for long context safety classification. Classifier context rot cannot be fixed by tweaking the monitor's weights. Securing these systems requires re-architecting the agent infrastructure itself. System architects must abandon the practice of final transcript monitoring. Waiting until a massive log is complete to run a single security check guarantees poor recall. The alternative is incremental monitoring. The system subsamples the transcript, isolating data up to the most recent tool call, and diverts that section to the monitor. By cropping the timeline here, the malicious action remains the most recent information processed, bypassing the middle context black hole. Executing this strategy safely requires developers to embed specific lifecycle hooks directly into the agent's core code. The Prime Agent framework utilizes a hook called Agent Settled. This breakpoint triggers only when the agent's internal loop, its retries, and its queued work are completely idle. Triggering the incremental monitor specifically at the agent settled state allows the system to evaluate actions accurately without interrupting core application flows or active Universal Commerce Protocol transactions. Explicit hard-coded architectural breakpoints are currently the only reliable way to enforce context discipline on infinite horizon autonomous agents. Incremental monitoring solves the architectural problem, but it must be paired with prompt-level interventions to maximize accuracy. The first tactic is injecting periodic, localized task reminders directly into the transcript, placing them exactly between a tool call and a tool response. The second is the chain of thought list strategy, which forces the monitor model into a highly specific reasoning budget. Before the monitor is allowed to output a final classification decision, the prompt forces it to explicitly quote the most suspicious actions it found verbatim. Agentic commerce and SaaS automation are rapidly transitioning to fully autonomous models, managing enterprise transactions at scale without human oversight. Raw hardware context windows will continue to expand, but true agentic safety requires treating the language model as a bounded component that requires rigorous lifecycle management rather than a flawless oracle.